Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications, Chapter 11, Python Analysis of Incomplete Climate Data, Part 1. In this video, we will learn how to visualize and read in space-time data matrices. Let's begin with our import list for Chapter 11. You will need to import the following functions in order to run the following code. We are going to be starting with figure 11.4 due to the fact that figures 11.1 through 11.3 are snapshots of the NCDC NOAA data access tool. Please follow the highlighted link for more information regarding these plots. Beginning with section 11.2, we're going to read in NOAAGlobalTemp, and we are going to look at the space-time data matrix given in this data set. We are going to have to open a .asc file using an open function with the file name, and this R just allows Python to know that we are only reading in this file. For .asc files, we do need to grab the data in a much different way than we would do with .nc files and Excel files. We're going to create an empty array named DA1, and then we are going to go line by line into the file, and we are going to strip and split each of these lines, which allows us to split up each line based on spaces, and then it will split them up into different data, into different columns within this DA1 array that we are creating. Then within F, in each of these stripped lines, we are going to append the float version of F to our DA1. Once running this for loop, we do get a length of DA1 to be roughly 4 million plus some. We're going to go ahead and print our DA1 0 through the third index. Next, we are going to create our time variables and name them TM1 and TM2. Both are going to be very similar ranges, and we are going to go ahead and print the length of these as well. We're going to extract the months using the following code. We're going to set up an empty array, and then we are going to go into the for loop that will append DA1 at index TM1 on every I in this for loop. These values will be appended to our empty array, which is MM1. We are going to set up and extract years in a very similar fashion, making that empty year array going into this for loop. This time we are accessing TM2 index in our DA1 data. Now we are going to combine our years with our months. We're going to name this array RW1, standing for row 1. We're going to enter a for loop, and we are going to append the string of each year, add a dash in between, and append the string version of the month. We're going to go ahead and verify that we have made the right RW1 variable by printing MM1 indices 0 through 6, year 1 indices 0 through 6, and printing the length of both of those. We're also going to go ahead and print TM1 indices 0 through 6 and TM2 indices 0 through 6. We're going to go ahead and create a TM3 data frame by concatenating our TM1 data frame with our TM2 data frame. And these are going to be concatenated across axis 1. We're going to go ahead and remove the months and years from the scanned data. We're going to open up this empty array and name it TM4. Entering this for loop, we're going to append TM1 at the arth index to TM4. We're also going to append TM2 at the arth index to TM4. We're going to go ahead and reverse our TM4 once this for loop has ran, and we're going to make a copy of DA1 and name it DA2. Then we are entering a for loop, aggregating through TM4, deleting our DA2 at every F index. This for loop will delete certain climate data from our DA2 copy, which will allow us to only look at the data that we need to look at. We're going to go ahead and print the length of DA2 divided by the quantity of 36 times 72. This will give us the months, which can be dictated by 137 years plus 1 month, January 1880 through January 2017. Now to generate the space-time data, we are going to set up this var variable, which will be the array of the arrays for 0 for x in range 1645. So we will have an array of zeros, and then within this array of zeros, we are going to aggregate for y in range to 2592. We are also going to set I equal to 0. Then we are going to go into our for loop, which will enter both of those lengths that we just made in our var variable. And we are going to set each indice in our var variable equal to the values that can be found in DA2 indexing at I. Our last line of this for loop will just index I by 1 in every single case. Setting up our DA3 variable, we're going to just make that var ND array into a data frame, naming our columns with that RW1 that we created above. Creating a lat1 and a long1 variable, we are just creating this line space for lat1. It will range in between negative 87.5 and 87.5 with 36 digits in between. And we're going to make this into a list by using a toList function. For long1, we are going to range from 2.5 to 357.5 with 72 points in between. We were also going to make this into a list format. We're going to go ahead and use the sorted function to make our next lat variable. We're going to be sorting the lat1, multiplying it by 72, and wrapping that quantity in a sorted function. For our capital long, we are going to multiply our long1 times 36 to get a desired length of our long array. We're going to go ahead and insert our lat variable at index 0. Next, we are going to insert our long variable at index 1. Then we are going to go ahead and create our space-time data and name it GPCPST. And this will be the concatenated version of our data frame of lat followed by our data frame of long, followed by our data frame on DA3. We are going to concatenate these on axis 1, which is the columns axis. We're going to go ahead and set the column names of this data set equal to RW1. Once we run this block of code, we do get all of our print statements to pop up. We can verify our lengths of our arrays that we made up ahead, as well as the first 6 digits in each array. Just a reminder that the first 2 columns are lat and long, ranging from -87.5 to 87.5, and then from 2.5 to 375.5. The first row for time is header, but it is not counted in our data. We could go ahead and save this data to a CSV with your desired name in there. We're going to save this data as NOAAGlobalT1.csv. This will allow you to grab the outputted data as a CSV file. Moving on to figure 11.4, we're going to go ahead and use that GPCPST data and create our data for plotting. We are going to go ahead and grab the string column name 2015-12, which corresponds with December of 2015. We are going to need to convert the vector into a long lat matrix for our contour map so we can plot it. We're going to go ahead and name this data map_mat, and it is going to be the reshaped version of our GPCPST data on 2015 December. We're going to grab the values and we are going to reshape it into the -1/72 shape. This will put it into the 36/72 shape using this command. We're now going to compress our numbers into the range of -6 to 6. The highlighted line will compress the numbers into the -6 to 6 range. We are using the maximum function, and we are also using the minimum function. We're going to go ahead and set some parameters for our plot. We're going to set DPI equal to 100. We're going to set up our PLT figure and name it Fig. We're going to go ahead and specify our DPI, which has to do with the fig size of our plot. And we're going to go ahead and add our axes. We could create a base map projection using a cylindrical projection. We're going to go ahead and create our map using the base map function on the cylindrical projection. We're going to name our base map instance DMap. On our DMap instance, we're going to go ahead and draw our coastline, draw our state lines, and draw our country lines. Continuing with our DMap, we're going to go ahead and draw the parallels that are on the range from -50 to 100 by 50. We're going to go ahead and label them as well as setting their font size to 15. We're also going to draw the meridians, which will be from 50 to 350 with 50 points in between, setting some of the labels equal to 0 or 1, which will dictate if they show or not, and also setting that font size equal to 15. Next, we're going to convert our latitude and longitude values so we can plot on the XY coordinate values. We will need to reverse the sequence of lat1. lat1 underscore rev will be equal to lat1. Then we are going to set x and y equal to our dmap function, where we are meshing together our grid for long1 and lat1 reverse. This will allow x and y to match up coordinate wise with long1 and lat1 underscore rev, but have each unique coordinate pair to be able to have a contour point upon it. We're going to go ahead and create our contour levels and call it C levs, which will be the NP arrangement between -7 and 7 by the 0.5 step. We could go ahead and print out the X shape, Y shape, and mat shape to verify that all of these shapes are matching up. We're going to go ahead and go into our contour function using that dmap was created from that base map. And we are contouring F on our X by Y by mat values. We're using levels equal to C levs, and our color map will be the jet color map. We do need a color bar on our plot. We're going to name it C bar, and it will be the dmap color bar on our CN plot with the location equal to right and a pad of 2%. This will make sure that we have a little bit of space in between our plot and our color bar. We're going to specify the specific tick marks we would like to see on this color bar, as well as setting the Y labels equal to the strings of those tick marks. We're going to add some text, which will be a degree C symbol over the color bar. We're going to go ahead and add a plot title to our plot, as well as a X label and Y label. Wrapping this whole block with a PLT show, we do get this NOAAGlobalTemp anomalies degree C for December 2015 plot. We can see that we do have a little pad between our plot and our color bar, as well as having a jet color map overlaid on our contour plot. Moving on to the next plot in this sequence, we are only going to keep the data for a Pacific region for years between 1951 and 2000. We're going to go ahead and get the data for region that is -20 less than latitude. We're going to go ahead and get the data for a region that has latitude greater than -20 and less than 20, as well as specifying our longitude values between 160 and 260. We're going to name this slice of data N2, and this is how we slice it according to those lat and long values. We can go ahead and use the ampersand in between each of those slices to make sure that you need to meet all of these conditions in each row of your GPCPST dataset in order to be in this new N2 variable. We could go ahead and print the size of our GPCPST data as well as our N2 size. We are going to only be looking at the January 1951 data, which starts at column 854. We're going to name this Pacific DAT, and it will be the N2 data located on all rows, but only columns between 854 and 1454. When we run this block of code, we do verify that our GPCPST has shape 2,592 by 1,647, whereas our N2 has shape 263,520. Moving on to figure 11.5, which will be this zoomed in on the Pacific region plot. We're going to set up a latitude variable and a longitude variable, as well as using a PLT close function. We have not seen this before in our tutorial series. This just allows us to reset Python's plotting mechanism to make sure that we don't have any competing information going on. We do need to get the December 1997 data from our Pacific DAT data frame. We're going to go ahead and name this map mat, and it will be the reshaped version of that Pacific data, grabbing the 1997-12 column and grabbing those values found in there. We're going to reshape this to the 8 by -1 size, which will result in an 8 by 20 matrix. We're going to go ahead and set up our figure using those DPIs that were defined up above, as well as adding our axes, which we would like to view on our plot. We're going to create that map using the base map cylindrical projection. Go ahead and draw our coastlines as well as our country lines on this map. We're going to go ahead and draw our parallels and meridians dictated by the two following lines. We will have our parallels spanning from -40 to 60 with a step size of 20 in between. Our meridians are going to be arranged from 50 to 350 with a step size of 50 in between. Both of these font sizes will be 15. We do need to convert our lat and long values to be able to plot them on our base map. We're going to just name them X and Y, and we go into that base map instance, and we are going to mesh together our long and lat that we created up above. This will allow us to have every unique pair between each longitude and latitude value. Go ahead and set up those contour levels. Using the NP arrange function, we're going to span from -4 to 4.2 with a step size of 0.1. Finally, filling our contour map with that contour F function. Our contour map will be filled by the XY axis with map mat overlaid on it, using levels dictated by CLevs and using the jet color map. We're going to add our color bar using that pad parameter once again, specifying our tick marks. We're also going to add the degree C over our color bar and our title to the top of our plot. Lastly, setting our X label to longitude and our Y label equal to latitude. Wrapping that with a PLT show, we do get the tropic-specific SAT anomalies for December 1997. We can see that we have a zoomed-in region of anomalies printed on this map, and we are not including any other data that is outside of our ranges that was specified at the top of this block. This concludes Chapter 11, Python Analysis of Incomplete Climate Data, Part 1. In the next video, we will learn how to compute spatial averages and observe their trends.